Hello, everybody. Time to look at some notes here for physics. The idea today is to look at rotational dynamics and inertia. So in our packets, we're looking at day four notes here, the rotational dynamics and inertia. And that is going to pick up on page 19. All right. So the big picture from this is figuring out how inertia and acceleration work together for systems, rotating systems. So let's jump right into it here. So the big idea is this is application of torque. We've talked a little bit about torque already. Oh, wrong notes, not rolling motion. That's wrong. There we go. One of the big aspects of rotational dynamics is torque. Torque is the key to understanding how these systems are going to work, because it really is torque that causes acceleration. In a linear system, there's an underlying force that applies your acceleration for an object. The force specifically for a rotating object is torque. So the torque causes the angular acceleration, and the tangential and angular accelerations are equal to the force being applied to your mass. And so this is a system. You have a pivot point, and you have the tangential acceleration happening as it increases in the angular velocity. So it's actually is speeding up more radians per second. And there's a torque, there's a tension force, which is a capital T, that's keeping the object from breaking that centripetal acceleration. And then there's a torque applied to the object to get it to increase its speed around the circle. So there's two different accelerations happening, and you don't want to really get those confused too much. One is the tangential acceleration caused by an increase in the force, which is torque basically, and the other one is the one we know about already from before, the centripetal acceleration due to it changing direction as it's rotating around the circumference. Okay, so torque is a relationship of the radius times the force, and in relationship to the angular acceleration, we see that it's related to that concept. You can see torque is there, and we have the mass and the radius of that mass squared. So for rigid bodies, which of course are all the rotating systems are based on these rigid bodies, we have kind of a complex system where you could have masses spread out, evenly distributed through a weird shaped object, or you could have like a collection of masses attached together with thin light rods, they would call them. But what we need to do is look at how the torque is effective, with those different, positions. So in a normal rotating object, like a bicycle wheel, there's a lot of parts to that. There's spokes, there's the rubber, there's the metal rim. And so it's a very complicated system. So how we have to apply that idea is we have to actually calculate the torque on each particle. With a wheel, that doesn't really work, but in physics world, we have a lot of more simpler devices that we're going to look at. So each mass in a system like this is going to exert a torque on its motion, and those are all going to be separate forces. Well, how do we calculate that? Because they're going to act together because they all have the same angular acceleration. So how do we calculate that? We have to apply the concept of torque. So for these objects, in order for them to actually apply the torque, we have to know a couple things about them. We have to know their radius and their mass, okay? In terms of the torque for these particles, if we add them all together, if we add the net torque of all these together, they have all the same angular acceleration. So for object 1, it's mass times its R value squared times the alpha. For torque 2, same thing, just mass 2, R2. But it's all the same acceleration. So if you look at the net torque equation, the net torque equation is really an application of all the torques. You can see that you can factor out your angular acceleration so that the angular acceleration is separate from the equation. So really what it boils down to is they all have the same amount of angular acceleration, and that proportionality, that constant between all the accelerations of all the parts and where they are, that's known as inertia. That's what inertia is. It's the proportionality between all the parts that make up an object. Okay, so the concept is that by rotating an object, all the masses work together to affect the acceleration, how hard it is to accelerate it. So like this wheel has a specific moment of inertia that makes it difficult to spin because all the weight is basically around the outside edge, okay? And that's why it has weird units. The moment of inertia is actually measured in the weight and the spacing. So you see it's in kilograms times meters squared. Meters squared being, you know, a two-dimensional surface area kind of thing. So it's how the, excuse me, how the weight is separated across that space. And a big factor in this, and you'll see in a minute when we do a couple problems, is that it really depends on the axis of rotation too. How is it being rotated? So this is the whole equation then. So we can calculate the angular acceleration of a rotating object by looking at the net torque, dividing it by the inertia of that object. So a net torque is the cause for angular acceleration. Angular acceleration is the torque applied to an object of known inertia, and that's your acceleration. So if I, you know, applied a torque to this, you know, a certain amount of torque, keeping it constant, you can see that the wheel speeds up, speeds up, speeds up. It's got a defined moment of inertia, and as I apply that same amount of force energy, the same amount of torque to that system, it's going to speed up and speed up and speed up. And before I know it, I'm doing sweet jumps on my bike, you know, going looking fast, hitting all the jumps. So that's the idea there. So a good conceptual way of looking at it is merry-go-rounds. You know, we don't have to watch the fail merry-go-round videos again probably, but they're probably fresh in your mind. And you actually have a pretty good concept of moment of inertia if you think about systems like this, because you can relate the organization of the mass to this merry-go-round situation, where if you have a lot of people sitting on the outside edge of a merry-go-round and you push it, it's very difficult to make it accelerate. Whereas if everyone is in the center, it's much easier to get it to speed up. So let's say you can push with a certain amount of force, you know, like the maximum amount of force you can push the merry-go-round with. If everyone is on the outside edge, you're going to have a really hard time getting it to speed up unless you're Quinn. You can run really fast. But if Cecilia was pushing the second one and doing her perfect race walking form, you know, it would get going wicked fast because all the weight's in the middle and your force is going to be, well, your force is the same, but the acceleration due to your force is going to be much greater because the inertia is different. The inertia is much less. Okay, so zipping back just for a second, because the inertia is the denominator of the equation, if you can apply a certain amount of torque, and that's a constant, and your inertia is smaller because of the organization of the mass, acceleration is going to be much greater. So, you know, they take that into account when they're designing things. You know, if you have a tire on a vehicle and the tire is massive and has clunky tread, and you know the tire itself is really heavy, it's going to be hard to accelerate that wheel and make your car go fast, right? So they might use like composite rubber, maybe thinner sidewalls, try to cut down on, you know, the inertia of the wheel so that the torque that the engine applies is able to accelerate it that much faster. So, and the merry-go-round is the same idea. If the weight is more centralized, then the inertia will be affected, and it's going to be easier to spin something if the people are sitting closer to the center than if they're sitting on the outside edge. We've seen a lot of these diagrams before, but this is the relationship between the linear and rotational systems. The linear and rotational systems do align pretty nicely. Force is something that we measured for our linear systems, excuse me, and that's torque in the rotational systems. Mass is not mass anymore. It's the spreading out of the mass. It's mass over area for a rotating system. Acceleration is angular acceleration, and we can find the acceleration by looking at the torque applied for the inertia instead of force applied to the mass. Remember, before Newton's second law was F equals ma. F equals ma is now torque equals alpha inertia. So it doesn't roll off the tongue as easily, but Newton's second law still applies here with that idea. Okay, so let's look at a sample problem here. So let's say we had to calculate the moment of inertia of this weird art project, which must be modern art because, I don't know, not that appealing. Physics art usually isn't that appealing, right? So what we're going to do is we're going to rotate this sculpture in two different ways. So you can see in the first case, we're rotating along this axis, axis A. So the object is the L-shaped object. Okay, this is our L-shaped object. Is rotating like this way. Okay, this is your pivot here. I'm sure that's easy to see. And then in B, we're rotating it along this way. Okay. So, and this is physics world. This is a new one for us, I think. But the masses are connected by very thin rods that are all uniform lengths at 10 centimeters. And what we want to know is we want to calculate the inertia of those two different scenarios. Okay, so let's look at that together here. So like I mentioned, in one way, it's being rotated about this side, like this. Okay, and then A way is rotating like this. so this part is staying still. And then for B coming out, it's actually going like this around that point. So we're going to look at both A and B, try to make sense of what is going on there. So the calculation is your inertia of that rotating system is equal to your masses and your radius squared. Okay, and you have to add those all up together. So one of the tricky parts is to figure out how far they actually are from that axis of rotation. Well, for axis A, this position is 0 for the 1 kilogram weight because it's actually on the axis of rotation, axis A. Okay, so that one is going to have a 1 kilogram, but it's multiplied by 0, so 0 squared. Mass 2 is over here. That's 10 centimeters from the axis of rotation. So that one is going to count. So those are kilograms. Let's convert these to meters. 10 centimeters is 0.01. And then mass 3 is 1 kilogram. And it's actually, if you measure it from here to here, because this is the axis of rotation, that's not a real rod. Let me dash it. That's actually still 10 centimeters away from that rotation. So it's multiplied by 0.01. Okay, that should be equal to our inertia of that system. So let's see how it adds up. Yeah, 10 centimeters, sorry, 0.1. 10 centimeters, okay. So this is 0, and then we have 1.5 times 0.1, but that has to be squared. 1.5 times 0.1 squared, plus 1 times 0.1 squared. Gives us 0.025. 0.025. Okay, and this is inertia we're talking about here, so it's the mass over the area. So it's got units of kilograms meters squared. Okay, so that's for axis A. Let's look at axis B together. So for axis B, because it's rotating about this point, we do need to use this other distance here. So because if it's rotating from here, it's they told us that this distance from here to mass 3 is 14.1 centimeters. Okay, this is still going to be 10 centimeters, but this is going to be different because it's rotating this way now instead of this way, if that makes sense. So for axis B, setting up our equation, for the first position, the inertia is still going to be 0 because it's right on the axis. It's got a mass of 1 kilogram, but it's at 0 meters. Mass 2 is still at, oh man, I forgot to square the radiuses in the equation here, didn't I? It's a miracle I did that on the calculator. That has to be squared. And then the last one is 1.0, and now it's got a distance of 14.1 centimeters. So that's 0.141, I guess it do, 141 squared. Okay, so that is zeroed out. Then we have 1.5 times 0.1 squared plus 1 kilogram times 0.141 meters squared. So you get a inertia of 0.0349. I'll call it. I'm rounding up a little bit, but you can see 0.034881. I'm rounding it up to 0.0349, or maybe 35. That will match the other one for significant figures, and that's kilograms per meters squared. All right. So they're small numbers, but you can see that it's actually harder to rotate axis B compared to axis A. Axis A has a lower inertia than axis B. So if you're making this weird art project that arguably is an art, you would want it to be probably this scenario, unless you had like, I'm thinking of, you know, does it even spin? Can't check now because it can't be in the school, but there's like a kinetic sculpture in the foyer outside the office that's supposed to be like solar powered and it like spins. That's pretty much this art project, I think. You know, and if you undersize the motor, maybe it doesn't have enough force to actually overcome the inertia of that. I don't know, it's kind of interesting to think about, but we're not paid to think, so. Where did my notes go? There we go. All right, so let's skip ahead a little bit. All right, so here are some different examples of the moment of inertias for different objects. And we kind of did a comparison, if you watch the video, of me and my sons rolling things down a ramp between solid spheres, hoops, and disc or cylinder. Those are the big ones. I don't see you really trying to rotate a slab. And there's different ways to rotate those too, right? So if you have a rod of any cross section and you're rotating on the end versus in the middle, they all have different known inertias. So what they had to do to, you know, work this out is figure out the inertia for these objects and apply it to any mass or length. So that's why there's a fraction there. The interesting one is a cylindrical hoop. Cylindrical hoop has an inertia of just the mass times the radius squared, that's it. And that's because all the weight is centered on the very outside edge. So it isn't a fraction of weight for that cylindrical hoop. You can see that a cylindrical disc is 1/2 the mass, because the mass, the way it's spread out through that disc, you know, it's got essentially half the weight, rotational weight, compared to the hoop, which makes it way easier to speed up. And then if you look at a solid sphere, it's 2/5 the mass. So the sphere should accelerate the fastest because it has the smallest inertia. Okay, so that's why we had the results we did down the ramp, because the sphere has 2/5 the mass compared to the cylinder, which is 1/2 the mass, compared to the hoop, which is all of the mass comes into play. The one that's kind of interesting is a spherical shell, like if you had like an eggshell kind of idea where the whole inside is hollow. It's 2/3 mr squared, so it falls, you know, kind of in between all of those, which is kind of neat. All right, so I don't know if you've ever seen this before. It's kind of a crazy sport. They I don't know, it's just like a strongman competition thing. I'm not really sure, but they have I think it's pronounced saber toss or caber toss maybe, and to show how strong you are. Oh, Scottish games. You can run with this pole and like throw it, and part of the strategy is to have it land on the end and have enough of the like rotational inertia to like follow through and flop on the ground. So you're basically throwing a tree, and you're trying to throw it as far as you can. It's kind of like a weird javelin kind of event. So the pole is 79 kilograms and has a length of 5.9 meters. And in this scenario, the gentleman threw it, and it has an angle of 25 degrees off the vertical when it touches the ground. And we just want to figure out the angular acceleration. So we know a lot of different things about it. We just need to apply those to the angular acceleration. Okay, so that's what the second board is for here. Oops. All right, so here we have our illustration. The ground is here. And we're going to be applying the idea through two equations. One is the torque, because there's torque at play with the caber or saber. And we're trying to find acceleration, which has torque in it, and it has the inertia as well. So we will be using the inertia that we had in the diagram here. Okay, so on the end though, this one, and we'll be using that in our calculations here. So kind of complex actually, because the weight is going to be pulling straight down gravitationally, so it's going to be plumb. It's going to be pulling straight down. But the torque is always applied at a right angle to the lever arm. Okay, so it's actually like a component type of affair with the wood there to measure that. Because your torque is really just supposed to be force times radius, but the force has to be perpendicular to the radius of that object. Now, this is a uniform cylinder, we'd call it. So it does have a center of mass in the middle that is, that's what's applying the torque. It's as if all the weight of the wood is located in that one spot here in the middle. That's going to be at half of that distance. So 5.9 divided by 2. That's at 2 point something. 2.95. So that's your radius, is 2.95. The problem is that 79 kilograms is not the full mass that's pulling on this object. We're going to have to figure that out. But the torque that is applied by this is equal to your force, which in this case would be the weight. And that's going to be multiplied by r, which we know is 2.95. Now it's the perpendicular weight force though, so I put a little perpendicular mark there just to indicate that that's what's going on. And what that really means is that it's the torque applied by the mass times gravity times sine theta. Times the radius. Now sine theta is in there because it's not the full thing, it's the component of that, of the weight force. Okay, so the weight force is pulling straight down, but there's a part of that, there's a component of that that's pulling perpendicular to that. So let's go ahead and calculate that, because we have all the the numbers and values in there. So the torque is equal to 79 kilograms times gravity times sine of 25 degrees and the radius is 2.95. Ran out of room there, but the radius is in meters. So, all right, let's see how we did. So we got 79 kilograms times the acceleration of gravity, 9.81, times sine theta, which is 25 degrees, and multiplied by our radius in meters is 966. All right, so let's think about the units. So we have kilograms in there, meters per second, and meters. So it's actually going to be newtons that torque is measured. Because we have kilograms, meters squared, seconds squared is a newton. Okay, so that's 966 newtons. That's going into this equation here because that's what we're trying to find is your acceleration due to that torque. So, so 966 is your numerator, and the inertia of this system is for a thin rod of every cross section rotating about the end is 1/3 mass times length squared. So let's put that into our equation. So we're looking for alpha. And we have our torque already. And our inertia is, what did I say, 1/3 ml squared. All right, in this case, because the L is actually the full length of this, it is the 5.9 meters that's squared. You can see in the illustration of the inertias of different objects, they are measuring the full length of that. So, all right, so let's put that all together. So we have 966 newtons, and we have 1/3 79 kilograms, and the full length was 5.9 meters, and that's squared. So we have 966 wow, what is that? 966 divided by, there we go, 1/2 times 79 times 5.9 squared. So we're looking at 1.1 radians per second. And why is it radians per second? So in the denominator, you can see that we have kilograms and meters squared. So the kilograms and meters squared is going to cancel out from the newtons, which had kilograms, had meters squared, and seconds squared in the denominator. So that cancels out, and we end up with radians per second. So that's how quickly it will be rotating or accelerating through, moving forward. Okay. Oh, what the heck? 1/3, sorry, not 1/2. I changed the inertia there for a second. Okay, so that's our acceleration, our angular acceleration. So that's going to, try to get it to flop over there, which is what you're going for, I guess, if you're, trying to throw those things. All right, hopping back into the notes. So how did we do? They always overcomplicate things, I swear. So they didn't calculate the torque separately. It looks like they mashed the two equations together boy, where did the square go for them? Oh, they canceled out one of the lengths. That's pretty tricky. Interesting. Okay. That's interesting. So yeah, we got the same result, but a little bit different application there. All right, last sample problem here. So this is extremely dangerous, but one of the ways they would start planes is just push on the propeller. So with an airplane, obviously that's a bad idea because you could get chopped up to death. But you could start a motor essentially by grabbing the prop and pulling it. Not advisable. It's like they used to start cars with a crank too, and people would grab the crank and try to crank it, and it would, the engine might backfire and just break your arm. So in this case, you could just fall into the prop and get chopped right up, which would be awful too. So, so here we have an engine of a small airplane is specified to have a torque of 500 Newton meters. The engine drives a 2-meter long, 40-kilogram single blade propeller. On startup, how much does it take the propeller to reach 2,000 RPM? So we're going from 0 motion all the way up to 2,000 RPM. So our blade is 2 meters long. Has a mass of 40 kilograms. And the axis of rotation is right through the center. All right. Oh, and we are going from 0. Oh, wait, we know a couple other things. We know the torque, so we don't have to calculate the torque, is 500 Newton meters. Newton meters. Did I miss a meter over here? Probably the distance. Dang. So 500 Newton meters, and the engine is getting up to 2,000 RPM. So our angular acceleration, we're going from angular speed of 0 to angular final speed of 2,000 RPM. It is kind of a pain in the butt, actually, that they're measuring that in RPM, because the, we always have to do a conversion. If it's in RPM, one of the first things we have to do is get it into radians per second, because RPM is not really what we're going for there. So it's not in the SI unit. All right, so one of the things we have to do about this is find the, look up the moment of inertia for a thin rod, because we're going to pretend it's a uniform thin rod, which has a moment of inertia of, what does that say? 1/12 ml squared. And we know the length of the, and the weight. So let's go ahead and calculate that first. So the mass is 40 kilograms. And the distribution of that over 2 meters squared. Okay, so the distribution factor is really small, right, at 1/12. So that's kind of interesting. So 1/12 times 40 kilograms. It's a pretty heavy blade, actually, times 2 squared, 2 meters long squared. Gives us an inertia that you're trying to speed up of 13.3. All right, so that's kilograms meters squared. So yeah, distribution of weight over an area. So what's our acceleration going to be? How quickly can this alpha here? If you remember from before, the acceleration is torque over inertia. So our torque and inertia are both known because our torque is 500 Newton meters. And our inertia is 13.3 kilograms meters squared. So we'll do 500 divided by that, and our acceleration, our angular acceleration is 37.5. And that, let's see, that has, because newtons is kilogram meters per second squared. So meters cancels out, and kilograms cancel out. Well, one of the meters cancels out. Seconds is still there. Oh, there's another meters right there. So meters is totally gone. So yeah, it's going to be acceleration in radians per second squared. So radians, being how much area covers, and second squared because it's an acceleration. It would be second squared, just like acceleration due to gravity is meters per second squared. Same idea. All right, so that's not the final result though, because what we're looking for here is to see, using that acceleration, how quickly it's going to get to its operational speed of 2,000 RPM. So let's do a quick conversion on that to get it out of RPM. Now, if you remember, we're trying to get to the speed of 2,000 RPM, which is equal to 33.3 revolutions per second. And using our kinematic equation that uses acceleration, we can see here that the angular acceleration is equal to the change in your speed over time. Okay, so that solve for time is going to be time is equal to the change in your angular speed over your angular acceleration. Now, delta W really means that it's looking at the final minus initial. So it's the final speed minus your initial speed over your acceleration. But initially it's 0, so that's gone. So the final speed is the 33.3 revolutions per second. And our calculated acceleration was 37.5 radians per second squared. Okay, so take the 33.3, we'll divide that by the 37.5, and we get 0.88. This is not right, actually. That's revolutions per second. Oh, gosh darn it. So that's actually equal to 209 radians per second. All right, let's try that instead. 209. Yeah, so that comes out to 5.6. 5.6. That's 9. 5.6 seconds. Okay, so the, that's the numerator. Oh my gosh. All right, we'll get this right. 37.5. 209. That's, all right, that's going to cancel out. Radians, that's why it wasn't working before. Radians cancel out. One of the seconds, one of the per seconds, cancels out, so it just comes out to seconds, which is good. That's our time frame. So, and the 5.6 is right. I did it right on the calculator for some reason, but on the board I wrote it down wrong. Go figure. I don't have Sam to correct me in the moment, but anyway, so hopefully those notes were helpful for you. We have pulleys still. So generally, pulleys follow the same kind of logistics. And another physics type thing that happens with pulleys is that the rope's not going to slip. So the pulleys have a rope that's got perfect friction, I guess, and it will match exactly how quickly the rim is accelerating. And we can forward those pulley systems with an object attached to it. You can think of it like a lever. Like that's what's applying the torque is the mass on the rotating object. So you have a radius of that pulley, and the speed of the rope is therefore going to exactly match the speed of the rim of the pulley. And the object falling is also going to have the same speed as the pulley because it's not going to slip. So in that case, then the velocity of the object is going to be equal to the rotational speed of the rotating object times the radius. And the acceleration of the object is equal to the angular acceleration of that pulley times the radius of the pulley. So you can convert between the two pretty easily. So if you're dealing with pulley systems, that's a good way to look at it. So anyway, hopefully that was helpful. We'll have a little experiment with torque in the torque lab, which we'll talk about here in a little bit. But thank you for joining me today, and we'll catch up with you guys later.